This is a website, a Wikipedia website that has some stuff on naming conventions if you want some place to review, since we don't really have a text per se. Nomenclature, again, is just a system of words used to name things in a particular discipline. We've already encountered some of the nomenclature that we use in pulmonary medicine, capital P, capital A. Those all have specific things that we use them for. The name of a compound should be enough information so that we know what the chemical structure is like, and we know that there's a lot of chemical compounds. Two different groups. We have ions, which are basically ones that are either free in solution or awaiting another reaction to become a complete compound. And organic compounds, or compounds, can be organic or inorganic in nature. We're not going to fiddle with the organic compounds so much as a lot of the inorganic ones. But they can be either ionic or through covalent bonds making molecules. Okay, let's talk about the simple ions first. Simple ions, where they're representative, meaning they're from the left side of the table, okay? They're not the transition, which is that middle portion. The way we name these, very original. We identify the metal. We add the word ion. Potassium, ion. Magnesium, ion. Beryllium, ion. Seems pretty simple, right? Gets a little bit more confusing when we have these cations that have multiple forms, and the transitions can do this based upon how many electrons they have donated to a reaction. And the way we know this is because of the Roman numeral that is present. So, for instance, here I have the metal chromium, Cr, and because it's donated 2 electrons, it's chromium 2. If it had donated 3, it'd be chromium 3. Okay? And these are just some rare transition metals that we end up having. Probably the biggest one we'll come across is iron. So here's our representative. These are our representative cations on the left. So again, calcium ion, lithium ion. And these are our transitions. Here's chromium. Here's iron, cobalt, nickel, copper. Anions, on the other hand, are a little bit different. It's not as simple. Well, it's still simple. We replace the ending of the element with the suffix IDE and add the word ion. So chlorine, it's not chlorine ion, it's chloride ion. It's not bromine ion, it's bromide ion. So what would Na plus be? Sodium ion. Seems pretty straightforward. Al3 plus. Aluminum 3 ion. That should be a 3 in there, by the way. Shame on me. Chromium 3 plus. Chromium 3 ion. How about Br minus? Bromide ion. Got the gist? Those are the easy ones. Now we get the not so easy ones. These polyatomic beasts. These are ions that have more than one atom. So they're, in this case, carbon and an oxygen. Almost all of them contain oxygen as one of the elements that are part of that polyatomic ion. Most of them are anions. There are a few cations, but for the most part they're anions. And there is no easy way around this other than memorization. Those of you who had chemistry before, am I lying? No. It just sucks. That's a medical term, by the way. Yeah. First two. NO2 minus is nitrite. NO3 minus is nitrate. Why? Because. Don't have a good reason for why that is the way it is. One of the few positive ions we'll come across is ammonium ion. Okay. Bless you. You may not know this, but this is ammonia. Add an extra hydrogen ion on there and it becomes ammonium ion. PO4 minus 3 is a phosphate ion. Why we add an H on there and it becomes hydrogen phosphate, don't know. You add two of them, becomes dihydrogen phosphate ion. CO3 minus is carbonate ion. Add an H, you would think it would be hydrogen carbonate ion, but of course not. That'd be too easy. It's going to be bicarbonate. Well, bicarbonate, but there's only one. Sorry, it's bicarbonate. Just like we had nitrate and nitrite and nitrate, same thing here. I have sulfite and sulfate. The good news is they follow the same pattern. You have one more oxygen molecule, one more oxygen atom present, and it goes from I to A. Same thing here. It goes from sulfite to sulfate. And of course, when you add a hydrogen ion to that, it's not hydrogen sulfate. That'd be too easy. It's bisulfate. Although hydrogen sulfate would be acceptable also. OH minus hydroxide, that beast, CH3CO2 minus, acetate. Cr2O7 minus 2, dichromate. Who comes up with these? The one you'll want to take at the end of this module, the cyanide ion. OCl, hypochlorite. And the one that I like, just because I think it's a cool name, permanganate. Sounds like it should be, a martini or something. Permanganate ion, MnO4 minus. Manganese and oxygen combination. What about if these polyatomic ions are located inside of a compound? Well, first step is we look at the one elemental ion plus a polyatomic ion. So there's something that's kind of by itself and then the polyatomic ion. So I named an ion, then named the polyatomic ion. Since these are normally negative, we're going to be naming the positive first. So here I have magnesium sulfate. Notice that the magnesium ion, the ions drop because it's no longer an ion. It's now part of a compound. Nope. If I have multiple things there, the more positive portion of the compound is named first, which usually is the metal. If there is a positive polyatomic ion, that would be named first. And hydrogen, which is kind of, although it's with the metals and it donates a hydrogen ion, it's kind of, or donates an electron, it's kind of by itself there in a lot of these. And then if it happens to be something where it's a nonmetal, whichever one is furthest to the left, so furthest towards the metal side. And then the negative portion is named last. So what would this first one be? Sodium nitrate. NaHCO3? Ah, that was an easy one. Sodium bicarbonate. Put it in your refrigerator and it takes away smells. Next one? Yep, just calcium nitrate. The fancy parentheses and that, if we go back and look, this NO3 is a minus. Calcium has a +2. So I'm going to need two of these beasts to be able to neutralize that calcium with a positive 2 valence. How about MgOH2? Magnesium hydroxide. And finally, sodium hydroxide. Okay. Ionic compounds. What if I have one metal and one nonmetal that are bonding? This is what we typically end up seeing. Name the positive cation, the metal. Name the stem of the negative anion, add IDE. So NaCl becomes sodium chloride. It's pretty easy. Not sodium chlorine, sodium chloride. Some of the stems that you'll end up seeing, OX for oxygen, CHLOR for chlorine, etc., etc. So those are the stems that we're going to have with "ide" after it. How about CaBr2? Calcium bromide. KCl? HCl? Calcium oxide. When I have two nonmetals going together, I use the prefix of the first element, add the element name, use the prefix of the second element, use the stem of the second element, add IDE. What the heck is he talking about? Let me just give you an example, and I'll go back to where this prefix of the second element comes from, the prefix of the first element. P2O3, both of them are nonmetals, right? Relatively right side of the table. The fact that there's two phosphoruses means that I have to have a prefix telling me there's two of them, and the prefix is di. Diphosphorus, 3 oxygen, tri-oxide. So I basically just broke that apart. 3 oxygen combining with 2 phosphorus. And these are the prefaces, whatever. Mono, di, tri, tetra, penta, hexa, hepta, octa. Should look relatively familiar if you took geometry at all, except for maybe mono and di. Mono we typically drop if it's just the first element that we're talking about, but we always have it before the second element. If two vowels, that'd be really interesting. If two vowels appear together, drop the vowel from the prefix. And hydrogen is the first named element, never takes a numerical indicator. So regardless of how many hydrogens there are present there, hydrogen sulfide has 2 of them, still it's hydrogen sulfide, not dihydrogen sulfide. Example, the elements carbon and oxygen bonding together, carbon plus mono for 1 oxide, and it's not carbon monoxide, it's carbon monoxide. We just combine the 2 O's together. There are some exceptions, of course. We don't call dihydrogen oxide or hydrogen oxide, it's called water. Hydrogen peroxide is just kind of, again, where that peroxide came from, I have no idea. Ammonia we talked about, and of course our favorite gas, methane, CH4. And if you take organic chem, I'm very sorry for you, but you'll learn more about all the carbo that are there. N2O. You don't? No. Okay. So I guess you want me to just leave it there? H2O2 hydrogen peroxide, NH3 ammonia, CH4 methane. You don't need to know instead of, because we're not going to use them. How did that slip by? I must have added that on. Forgot to print it. I'm such a mess. Got it?
One more. And what's your favorite one?
Yes, dear. Ready? So, N2O. What'd you say, Becky?
I said nitrogen dioxide, but it's
Monoxide. Nitrogen dioxide would be NO2. Somebody know what N2O is? No, I'm sorry, NO2. That is laughing gas, yeah. Dinitrogen monoxide is a poisonous gas. Carbon dioxide and water. Don't let them kid you, dihydrogen monoxide. It's water. And I think this is where I'll stop.